Thank you for the introduction. So first, I would like to thank the organizers for this invitation. It's really a great pleasure to be here on this special occasion. Jean-Pierre has been a very generous mentor to me over the years, so I warmly thank you for that. So the main theme of my talk, which is a joint work with H.C.Lu from Marseille and A.Zeriahi from Toulouse. I will try that. So the main theme is about weak solutions to complex Monge-Ampère equations. And those solutions are usually produced by exhibiting many subsolutions and supersolutions to these equations. In principle, subsolutions and supersolutions are dual notions, one to another, but in reality they are not. And actually, producing supersolution is something rather difficult, and these objects in themselves are rather mysterious. So part of the talk is to try to explain the recent progress in the understanding of supersolution to complex Monge-Ampère equations. But before that, I would like to give you some geometric motivation for these issues. So let's start with mildly singular projective algebraic variety with a canonical bundle. And it is well known that a fundamental problem to try and produce singular Kähler-Einstein metrics in this context, so solution to this equation. This goes back when V is smooth to the fundamental work of Aubin and Yao. There has been since then several works, so I'm not going to recall the full history, but a bit more recently, the work with H.C.Lu and A.Zeriahi, in which we have produced such Kähler-Einstein equations, Kähler-Einstein metrics, in the context where V has log-terminal singularities. And more recently, the definite result sort of has been proposed by Berman and Guedj, where they have proved the existence of such Kähler-Einstein metrics when the manifold, the variety V has semi-log canonical singularities. So I'm not going to recall the algebraic definitions of all these types of singularities. Rather, I'm going to transfer to the analytic point of view. So solving this Kähler-Einstein equation is equivalent to solving a complex Monge-Ampère equation in the following way. So we first take a desingularization of V, and solving the Kähler-Einstein equation is then equivalent to solving the following Monge-Ampère equation. So it takes the form omega plus ddc phi. So ddc is a standard French notation for IDD bar. Let me recall that once and for all. Up maybe to a normalizing factor. So omega is the pullback of a Kähler form representing the first-chance class of Kv. So it is only semi-positive on the desingularization. And on the right-hand side, you have a term F, which is density whose properties depends on the type of singularities of the original variety. So for instance, F will be smooth on the pullback of the regular locus of V, and it will be continuous when you approaches the exceptional divisors in case the original variety has canonical singularities. If the singularities are a bit wider, so log-terminal singularities, then you end up with a density which is just a bit better than L1. In L1, epsilon. And the size of this epsilon depends on the log-canonical thresholds. And in the case of Berman and Guedj, actually the density is not even integrable. And it actually blows up. So the idea you should keep in mind is that if SE is a defining holomorphic section for an exceptional divisor, then F blows up roughly like SE to the minus square. Okay, so that's for the analytic point of view on these various types of singularities. And of course, due to the presence of these singularities, you cannot expect to have smooth solutions all the way down to the singularities. So we have various types of degeneracies, and it is very useful to produce various notions of weak solutions to these equations. And that's the main theme of my talk today. And basically, there are two types of weak solutions I would like to explain. The first one goes back to the work of Bedford and Taylor. So these are called pluripotential solutions. And more recently, since 10 years or so, Harvey and Lawson on one hand, and Philippe Sidieux, Ahmed Zahia, and myself have developed a notion of viscosity solutions to these equations. So the goal of today's lecture is to briefly recall both types of weak solutions and try to explain a bit how these two different worlds intersect. So first, I'm going to recall briefly the notions of pluripotential sub, super, and solutions, then do a similar thing for the viscosity world, and then try to explain the differences between these two notions, and how, once you understand a bit better this dictionary between the two worlds, it allows to produce a certain number of results. For instance, there is one type of result we obtain. If there is a subsolution to some of this degenerate complex Monge-Ampère equation, then actually there is a unique solution, which is, for instance, bounded globally on X, continuous on the locus of the class of omega. And moreover, this solution can be obtained as the quasi-parasomnic projection of the inf envelope of supersolution. So in talks on Wednesday morning, you have seen rather upper envelope of subsolutions. And it's kind of a challenge to actually approach this solution from above by using supersolution. What do you say? So this is the ample locus. So the continuity will be valid on some large Zariski open set, which is the ample locus of the cohomology class of omega. So if you like, in the geometric context I was mentioning, it will be on the regular part or above the regular part of the variety. Okay, so let me actually first recall what is a classical subsolution. So function which you expect to be at least a C2 smooth. And you say it is a classical subsolution if first condition, it is omega plurisobharmonic, meaning if omega locally writes as a DDC of a function rho, then phi is omega plurisobharmonic is equivalent to saying that rho plus phi is plurisobharmonic. So classical subsolution is a function that has this quasi-parasomnic property and which satisfies the differential inequality Monge-Ampère of this function is greater or equal than the right-hand side. Similarly, supersolution will satisfy the differential inequality in the reverse direction, but there is a plus here, meaning that you take actually the Monge-Ampère, saying the Monge-Ampère is 0 in case the Hessian has a negative eigenvalue. So that's what I just said. Oh, sorry? What is G? Yeah, so thanks. Thanks, Boo. So throughout the talk, I will either use the notation F or e to the G for the density. Thank you. So of course, the problem is that in this particular context I was mentioning, classical solutions actually do not exist. So we have to go beyond that. And let me now go to the pluripotential world. So let's take phi, omega plurisobharmonic and bounded. Then the Monge-Ampère in the sense of Bedford and Taylor is defined that way. You take phi j approximants that are smooth and decrease towards phi. And you look at the Monge-Ampère measures of those approximants. And then the theorem definition is that those measures, those smooth measures, have a unique limit. And this limit is the Monge-Ampère of this function. So I should stress that this definition or this point of view is actually local because we need to start the function. And it's, as we all know from the work of Jean-Pierre, it's very difficult to globally regularize such functions. Moreover, this measure that we obtain that way is independent of the approximant. And this Monge-Ampère operator is then continuous along monotone sequences, but is not continuous along, say, L1 convergence, for instance. And at the heart of this theory by Bedford So there are several maximum principles, and there is one that I would like to emphasize today, which is that if you take the maximum of two such functions, then the Monge-Ampère of the maximum is always greater or equal than the minimum of the Monge-Ampère of the functions. I see some experts a bit worried about this inequality, so so far the functions are bounded. So there is some hypothesis behind that. So actually this inequality is a consequence of a more precise inequality that I have learned during my master's thesis reading lecture notes by Jean-Pierre, which is the following. If you look at the Monge-Ampère of the maximum of two functions, then it's actually greater or equal than those two terms. And it seems somehow natural, but the main difficulty is that the functions that we are dealing with are not continuous. They are only quasi-continuous. And passing actually from continuous to bounded function is somehow the heart of the technical matter of Bedford and Taylor theory. So for instance, the set where phi is strictly less than psi is not an open set. It's a so-called plurifine open set. And that causes quite a lot of difficulties. Okay, so in this context, a pluripotential solution is a function which is, say, bounded and omega plus-harmonic, and that satisfies that its Monge-Ampère is again greater or equal than the right-hand side in this Bedford-Taylor sense. And a supersolution is something similar, but let me stress here that in this world, to be a pluripotential supersolution, we ask for the function to be omega plus-harmonic, which was not the case earlier. And a pluripotential solution is both a subsolution and a supersolution. Here are a few rather basic properties of those objects. So first, if you take two subsolutions to such an equation, then the maximum of those functions is again a subsolution. If you take a large family of subsolutions, then you can take its upper envelope. You are losing upper semi-continuity, so you need to take the upper semi-continuous regularization, and you end up with yet another subsolution. So it's the starting point of the classical Perron method to try and solve the equation. But on the other hand, if you take two supersolutions in this sense, then the minimum of those two guys is not a supersolution. Actually, the plurisonicity is broken by taking the minimum of those two functions. And a final word is again stressing that those functions are not necessarily continuous, but rather quasi-continuous, continuous in a weaker sense. So pluripotential subsolutions are actually the objects that are rather well understood. So here is a characterization. For simplicity, I explain this in a local setting, say in the domain of CN. So subsolution can be understood in the following various ways. This is a result that goes back actually to work of Botsky. So the following are equivalent. First, phi is a pluriharmonic solution in this sense, in this pluripotential sense. Secondly, you can actually take convolutions, standard convolutions of the function. You obtain smooth pluriharmonic objects, and those smooth objects should be classical subsolution of this regularized equation. And third point, if you actually try and interpret this equation rather in the distribution sense, then this is equivalent to the fact to an infinite number of subsolution properties. So the key to these equalities, to these equivalent properties, it goes back actually to the following classical observation that the nth root of the determinant can be understood as an infimum of tracing. And an important part of this equivalence in our recent work is that we actually leave the world of the pluripotential world, pass through the viscosity world in order to obtain these equivalences. Although in the statement of the theorem, there is no viscosity term involved so far. And then to pass, so we first treat the case of continuous object, and then to pass from continuous to more general object, we need to do some approximation process. And I will go back to this. This is an approximation process that had been designed by Robert Berman a few years ago. And I will explain it in more details a bit later. Okay, that's what I wanted to say about, or recall about the pluripotential world. So if you have a function which is upper semi-continuous and bounded on the Ampère locus, we say that at a point x0 we have a differential test from above if the following holds. So this Q has to be C2 smooth, and it lies above the function in the neighborhood of the point, and it touches the function at the point you are considering. So this is a differential test from above, and in blue color, you have the corresponding notion of differential test from below. Now, viscosity subsolution to such a complex Monge-Ampère equation is as follows. So you take a function which is bounded, upper semi-continuous, and you ask that for all points in the Ampère locus, and for all differential tests from above, the Monge-Ampère at the point of the test lies above the right-hand side. So you replace, so of course your function is not differentiable, your function u, and you replace the differentiability of the function u by differentiability of the test. So if you have never seen that before, it's perhaps a bit difficult to digest. What you should keep in mind for non-smooth function are the two following pictures. At smooth points, you can actually use the function itself as a test and play around with linear perturbation of the function, so you have plenty of tests. At non-smooth points, like this one, you start to test from below, like these ones. On the other hand, if the function looks like this, then there is no test from above. So the condition is void here, and you have something to check for those many tests, differential tests from above in this case. So I'm not recalling here, but which is quite important in the series, is that a basic fact of the series that there are differential tests from above at almost every point. So asking for these conditions everywhere is a highly non-trivial condition. So this is a viscosity subsolution. And a viscosity supersolution is somehow the dual notion. There is a little twist again, that the Monge-Ampère on the left-hand side is the Monge-Ampère plus. In case there is a negative eigenvalue, we say this guy is 0. And a viscosity solution is a bounded function on the Ampère locus, which is both a viscosity subsolution and a viscosity supersolution. In particular, on the contrary to the pluripotential world, viscosity solutions have to be continuous on the Ampère locus by definition. Here are a few basic facts, similar to the one for the pluripotential world. First, that's a good exercise. It's not a basic fact. It's an interesting exercise here with playing with the definition. If a function is C2 smooth, being a viscosity subsolution is equivalent to being a classical subsolution plus being omega plus harmonic. So the plurisubarmonicity property is encoded into this differential test that you are looking at. More formal consequence of the definition is that if you have two viscosity subsolutions, then the maximum is again a subsolution. And similarly, by duality, sort of, if you have viscosity supersolution, then this time the minimum is a viscosity supersolution, which was not the case in the pluripotential world. And therefore, if you have now a large family of viscosity supersolution, you can, which is locally uniformly bounded from below, you can take its lower envelope and get again a viscosity supersolution. Now, viscosity subsolution actually coincide perfectly with this pluripotential subsolution. So that's a result that we have obtained a few years ago with H.C.Lu and A.Zeriahi. So for subsolution, the two worlds do match perfectly, but the situation is actually more mysterious for supersolutions. So what we can get rather easily, through the so-called pluripotential comparison principle, is that if you start from a pluripotential supersolution, that its lower semi-continuous regularization is a viscosity supersolution. That's a easy exercise. The question is more in the reverse direction, and that's one of the results we obtained recently. If you start from a viscosity supersolution, then the pluripotential projection of this function is a pluripotential supersolution. So you look at all the functions that are omega pluripotential and lies below phi, and you take its upper semi-continuous regularization, then this guy here is a pluripotential supersolution. Okay, so I would like to say a few words about the proof. So first, maybe let's try to look at the simplest case where the function, so I wrote phi is C11 bar smooth, but you can imagine it is C infinity smooth. In that case, an important result of Berman-Demey guarantees that the projection is C11 bar smooth, so has bounded Laplacian. And therefore, you can interpret the Monge-Ampère of this function pointwise. And as I don't remember if that was in Tama's talk or in Valentino's talk Wednesday, the Monge-Ampère of this envelope actually vanishes outside of the contact set. And therefore, you have this identity pointwise. And now, since phi is supposed to be a supersolution, then you have an inequality for the right-hand side. And now, since phi and p of phi coincide on this contact set, you can replace phi by p of phi, this inequality. So for the regular case, at least it is correct, but it relies on deep results and on high regularity of the function, which is exactly what we want to avoid. So how can we go? How can we prove such a result when we are lacking regularity? I would like to stress the type of information that we have by now. So first, the function is bounded. So recall, phi is supposed to be a viscosity supersolution. So it is lower semi-continuous, it is bounded, and it is, by definition, a supersolution. The point that is still unclear to us is what kind of regularity is implied by the fact that the function itself is a viscosity supersolution. As I mentioned earlier, for a subsolution has to be omega pluripotential. In particular, it has some regularity. It is quasi-continuous. It has gradient in LQ for LQ strictly less than 2. You have some regularity information by the pluripotentiality. This information is not encoded so far in the fact that the function is a viscosity supersolution. But nevertheless, we are able to show this implication in the theorem. And here is the way it goes. So perhaps the proof is even more interesting than the result itself. So it relies on an approximation procedure designed by Berman, which was used also in Valentino's talk. So it goes as follows. Consider the following Monge-Ampère equation, family of Monge-Ampère equation, when J is go to infinity. So phi is the viscosity supersolution we start with, and mu is a shorthand for f dvx. So it goes back to some previous results of ours that there is a unique bounded omega pluripotential solution to such an equation. And we try to understand the behavior of this family of solutions. So first, the fact that phi is a viscosity supersolution implies that phi j lies below phi. In particular, if you replace this inequality in the Berman equation, you can bound from above the right-hand side by e to the phi j mu. Now, the second observation is that actually phi j is increasing, and it increases towards the pluripotential envelope of phi. By continuity of Monge-Ampère operators along such increasing sequences, you actually get the result. So how to prove these two claims? Here is just a brief idea of the way it goes. If in case the functions that we are dealing with are actually continuous, so a bit better than what we actually know. In that case, you can actually treat the e to the minus j phi mu term as a new density, which is a new continuous density. And you can observe that since phi is a viscosity supersolution of the original equation, it becomes, again, a viscosity supersolution of the Berman equation that you interpret in the viscosity sense. And therefore, the viscosity comparison principle tells you that phi j lies below phi. So phi is a super solution. The name is chosen in that respect. Phi j is the solution, so phi is above phi j. And similarly for the increasing property. So that's actually just a rough idea, because the real proof should take into account the fact that we don't know that it's a continuous. We have to do a double approximation process with some technicalities that you probably don't want to see today. But interestingly, this has motivated us to study more general this approximation procedure in more general context. So we have been looking, for instance, at this type of approximation. So now mu is a more general measure, so a probability measure which does not charge pluripolar sets. And phi, say, is a bounded Borel function. And then in that context, we have obtained the following results. The sequence phi j of solutions to such an equation converge to a generalized envelope, which is the following. So you look again at all the omega approximate functions that lies below phi, but you want this condition to hold true on only mu almost everywhere. And then the claim is that this guy here is, and again, some omega approximate function, and this is the natural limit of this approximance phi j. So the consequence of that, if you look at, we were dealing rather with a volume form or a slightly generalized volume form, is that those two, the generalized envelope and the original envelope, do coincide if you have a volume form and if the function phi itself is regular enough. So upper semi-continuous would do the job, or quasi-upper semi-continuous would be sufficient. But the bad news is that what we were interested in, viscosity supersolutions, they are rather lower semi-continuous. In particular, if you take the following function, so minus the characteristic function of some Borel set, which has 0 Lebesgue measure, but which is non-pluripolar, then the two envelopes do not coincide. And as a consequence, such a function can never be a viscosity supersolution of that type of equation. So we try to understand what is a viscosity supersolution, and a negative result, which is part of the understanding, is that such functions are never supersolutions of complex Monge-Ampère equations. Okay, I would like to go back a bit to the original geometric problem. So the result of Berman-Ganancia, as I already mentioned, tells you that when you work on a projective algebraic variety with semi-canonical singularities and ample canonical bundle, then there exists a unique singular Kähler-Einstein matrix. And the way it is proved is, as I briefly explained, by solving such a Monge-Ampère equation. And the original proof of Henri and Robert was to, so the density roughly looks like this. I already mentioned it. And the proof they use is by adapting a variational approach to this context. And in our recent work with Chin and Ahmed, we actually propose a different proof of this result by showing that the solution, the unique solution, is the lower envelope of supersolution. So just a few words about the proof, which actually treat more general equation. So the more general result that we obtain is as follows. If you have a subsolution to such an equation, so if you don't know what E is, just think bounded to C, then the lower envelope of pluripotential supersolution is the solution. So you take the infimum of all supersolution, and you take the projection, the omega approximate projection. And this is the unique solution to this equation. I would like to say a few words about the proof, very briefly. And again, an important observation is the following. If you start with two pluripotential supersolutions, as I mentioned earlier, the minimum of those is not pluriharmonic anymore, so it's not a pluripotential supersolution. But what we prove is that the projection of this minimum is a pluripotential supersolution to the equation. For continuous objects, if the density is continuous, if the function is continuous, you have all the elements in the previous slides to understand this. Namely, you start with those supersolutions, you look at their lower semi-continuous regularization. You obtain viscosity supersolution, you take the minimum, viscosity supersolution is stable on that operation, and then you take the projection. And if all those guys are continuous, then you actually go back to obtain the envelope of the minimum. Of course, for non-continuous objects, it's a bit more involved, and the proof relies actually on the following minimum principle. So if you take two bounded omega epsilonic functions, then the Monge-Ampère of the projection of the minimum is this time bounded from above by the maximum of the Monge-Ampère. So it's the dual inequality, if you like, to the one I mentioned earlier on the Monge-Ampère of the maximum. And interestingly, so this inequality has been first observed by Darvas and Rubinstein in a completely different context, when the functions were reasonably regular. And they have observed by looking at the geodesics in the class that the of the minimum is actually infinite along the going to call the definition of geodesics in a talk on Wednesday morning. And again, to prove this proposition, we go through an approximation process a la Berman. And that's all I wanted to say. Thank you.